Hey, good evening, everyone. Thank you all for coming tonight. I'm honored to get to talk to you all about a project that we've been conducting since about 2018 in southwestern Missouri for the Cave Research Foundation. And this was to figure out the watershed or recharge area for Roaring River Spring, which today is America's second deepest spring. Most projects don't occur just by one person, and this is just the case with this one. I'd like to acknowledge my co-author, Robert Lurch, Bob Lurch, a good friend of mine and scientific mentor. And we did this as a volunteer project because we felt strongly enough that this was a project that needed to occur, and there was a kind of a gap in the hydrologic knowledge of this area. Just a very brief little bit about me and Bob. My day job is as a Karst Hydrologist here at the USGS in Nashville. I specialize mostly in dye tracing and recharge area delineations, but I also work well with biologists because we both have sort of shared similarities in studying karst hydrologic environments. I'm also a big caver. I've been caving for over 30 years, and I do a lot of mapping. My co-author Bob is a retired soil scientist from USDA Agricultural Research Service in Columbia, Missouri, where he mostly focused on herbicide transport, row cropping, and water quality. He's very well published. He's also conducted karst studies at a number of different sites throughout Missouri. He's also been a caver and has led a number of different big survey projects. Now, kind of moving on to the topic at hand, just a very brief little thing. I think most people on the call tonight probably know what karst is, but we don't want to jump just immediately into the deep end. So karst is a landscape created by the dissolution of soluble rocks. So some soluble rocks that are pretty common are limestone or dolomite or gypsum or even salt. And in karst terrain, karst landscapes, there's a big connectivity that occurs between surface stream, surface hydrology, and the groundwater system. And as a result of this, any sort of activities that occur in these areas can have a direct impact on water quality in the groundwater system. Additionally, particularly here in the Southeast and in the Ozarks, our karst areas have biota that has a higher rate of endemism. So that means that we can find species that occur only in one site or a very limited number of sites. And also, karst areas are often very complex hydrologically. And so they require special tools to be able to understand what goes on in these environments. We can only access certain portions of the system. Here's just a nice view of sort of a cutaway view that Missouri Department of Conservation actually created years ago for one of their publications. And this works well because we're discussing Missouri today. And what you can see is that, we have a number of different inputs. We have bedrock that's below the surface. And then below the surface, we have all these inputs into our groundwater system. Some of them might be sinkholes, some might be losing streams, and all that works its way down into the groundwater system, but that can directly affect our water quality. And so you can see not only do we have sinkhole dumps or septic fields, but we also have groundwater wells that are pulling water out of the system as well. Now, I'm going to be mentioning a bunch of different terms throughout this evening, and I want to just kind of give you kind of a little brief intro of what these are going to mean because I'm going to mention them a lot. And so one of those is recharge area, and that's just a watershed for a spring or cave. Most of us have done, the watershed activity as a kid, where we would trace the upper point of the watershed and we'd come up with like what our watershed is. Well, a recharge area might actually encompass multiple little watersheds. We might be actually gathering together portions of different creeks. And so a recharge area, I'm going to talk about that a lot because that's what we were trying to figure out here for the spring. And that's just a watershed for a spring or cave. Delineate, that's just to define the boundary of an area. I'm going to talk a lot about losing streams. That's our primary mode of recharge for this area. And these are flowing streams that sink, or they might be dry stream channels, which contribute to these groundwater systems. I'll also probably use the term conduits. And you can kind of think of conduits as just sort of any opening. It may be big enough to walk through like a cave, or it may be something that's the size of your finger or the size of a pencil. And this is anything that can carry water rapidly through a karst system. Groundwater is any water which is underground, so I'm going to talk a lot about groundwater tonight. An aquifer is a water-saturated body of rock. And finally, faults are fractures in bedrock, which has had movement along that fracture. Another type of fracture that we see commonly in bedrocks are joints, and that's where we haven't had really any movement along that. And faults are going to play an important role in the hydrology that we're going to discuss this evening. So kind of just a little bit about how we kind of do some of this dye tracing. One of our main things that people ask us is, how do we detect this dye? How do we track this from point A to point B? Most people have seen dye injections, or they've at least seen the Chicago River on St. Patty's Day when they dye it green with all the fluorescein. But the way that we detect this is usually using charcoal receptors or packets, or what can even be called bugs. And these are little packets of crushed coconut charcoal. And we place these in either screening packets or milksock packets. The milksock are these little white packets here that look like tea bags. And we put those in the main flow of a spring or a cave or even a surface creek. And we have a whole network of these distributed across the area. And then we can change these at timed intervals to figure out how long it took the dye to get from where we poured it to where it ultimately came out. These gradually absorb dye over time, and so we don't have to be standing at the spring when the dye comes out, because the dye may come out right after a storm event, or it may be so dilute that we don't see any color by the time it comes out. So these allow us to monitor a wide network of areas, and also they're very economical, so we can have a broad network across the study area and not be sort of breaking the bank as it is. The way that we actually detect the dyes, we send these off to a lab. They pour a chemical onto that charcoal that pulls the dye off, and then they use an instrument that actually looks at the wavelengths of dye. And that gets on to our next subject, which is our fluorescent dyes that we use. There's about 5 different types of dye that we can use. And the most common that most people know is fluorescein, which is bright green dye, which you can kind of see in the background of the slide there. That's our most common one. That's what you see at the Chicago River. If you've ever had green beer on St. Patty's Day, you may have drank fluorescein. A couple others that we use are eosine, which is kind of an orangish green. I'll show you some pictures of that. We also use rhodamine WT. This is another very common one. We see this in a lot of different industrial applications. You might see it in various antifreezes or even the soaps at car washes. These days, rhodamine WT is nice because people are actually producing data loggers that can detect this dye. So we can actually put an instrument in the stream, and it will real time tell us what the concentration of rhodamine WT is. That can help us figure out when the dye arrived down to the minute. Additionally, we use sulfurrhodamine B, which is another kind of pinkish, purplish red dye. And finally, we can use an optical brightener called TINAPAL. And this is kind of an opaque white to bluish color, and it's commonly used in detergents. And so it's kind of what makes your whites whiter. Now, these names are a whole bunch of fun for everyone, but everybody really likes the pictures. And so this is just our dye injections. These are a couple different ones from across the state of Tennessee. But you can see fluorescein up here, this bright green dye. This is this orangish green eosine. We can see our rhodamine WT up here being injected into a cave. Here's sulfurrhodamine B, that pinkish purplish dye. And here's the TINAPAL OB, the optical brightener down here. Now again, each of these actually emit a different wavelength when they're analyzed with a laboratory instrument. And so that's how we can use these with the charcoal packets to map our groundwater pathways. Now then, how do we kind of take this information? Well, so this is a map of a bunch of dye traces that we did. The triangles that you see on the map, and we're going to see these all over the place tonight. These triangles are places where we put dye in. And then the blue lines connect us to blue dots where we had charcoal packets. And this allows us to sort of map that groundwater pathway. Now we can then take all this information and we can look at the watersheds that drain to each of these individual areas, and that allows us to delineate a recharge area. And so this is a nice recharge area for a big spring down in southern Tennessee. And then one of the things that we can really do with this is we can actually use that recharge area to then clip to land use and land cover data. And we can actually look back at previous land use land cover data, because this comes out about every other year or so. And we can look at changes in land use and land cover, and we can actually relate that to water quality changes that we might be seeing in the groundwater there. So knowing the recharge area of the watershed for a spring or cave gives you a lot of power to understand what's influencing that cave. Now, this is one particular system here. This is one delineated recharge area, but we can actually do studies on a larger scale, and we can actually kind of come up with a puzzle pieces of recharge areas, because in a lot of karst areas, it's all karst. All the water is going underground and flowing to somewhere. And so we really have lots of different recharge areas all across the different karst areas. And so this is kind of how we sort of start with an area and we sort of expand what we can learn about the area by working around the area using dye tracing. Now, next, I'm going to kind of give you a little bit about sort of the area that we're going to be talking about today. So this is Roaring River Spring, and we're going to get into why it's special here in just a second. So this is kind of the area. This is southwestern Missouri. You can kind of see the dot up here. It's right on the border with Arkansas. So we, of course, have our Arkansas map down here with a little dot. What I want to point out is you can see this big flat area kind of running right through the middle of this area. This is the undissected Springfield Plateau. And we're going to talk a lot about two different plateaus tonight. The Springfield Plateau, which is a younger plateau. The rock is a younger age. And then the Salem Plateau, which is a plateau that's lower in elevation and is older rocks. And we're going to talk about both those a lot today. Roaring River Spring is kind of located here in the east central of the map here. We're kind of closest to the town of Cassville here. Now, Roaring River Spring is the 18th largest spring in Missouri. It's the largest single spring in southwestern Missouri, and it's also the largest spring on the Eureka Springs Escarpment. Now, the spring itself is a water-filled pit 472 feet deep, which is currently the second deepest in the United States. Now, this was not the case when we started the project. When we started the project, the cave was only about 225 feet deep, and then divers were able to actually get through a restriction and explored an enormous water-filled dome pit that's on the other side of that squeeze, which went down almost to 500 feet deep. And it does keep going. The spring is also along a fault, and it discharges from the Ordovician, Jeff City, Cotter Dolomite. Now, its average flow can be over 100 cubic feet per second, but our base flow, when we don't have any rain at all, can get as low as 30 cubic feet per second, or about 19 million gallons per day. Now, the spring is the center point for Roaring River State Park, and this is one of Missouri's, if not Missouri's, top visited state park. I believe last year or the year before, it was the highest visited state park for the trout fishing that's there at the park. Now, it received a lot of press when the divers went deeper and discovered this enormous room that they couldn't see the walls of or ceiling or floor of. And suddenly our little project that we'd kind of been doing quietly off to the side got thrust into the spotlight. And they actually even did a nice article about us doing the dye tracing and our work. And this actually helped a lot with local landowners who had seen some of these articles and knew about the project and were very supportive of the project. This is a map of the spring. So the spring outlet is way up here in kind of the upper left. And then the old cave was right down here to this 225-foot restriction. That was all that was known when we started the project. But they got through that and then kind of came out into this enormous dome pit, which actually goes up above the level of the spring itself and actually has some air-filled domes at the very top, but keeps going at the bottom. And you talk to the divers, and when they got into this room, it kind of spooked them a little bit because the walls disappeared and the ceiling and floor disappeared, and it was just the enormous water-filled room down there. Now, even though it's very tall and very, very deep, if you look at it from a bird's eye view, it actually has a relatively small footprint. You can see that this is kind of just a slice down immediately into the earth there where all this water comes up. Now, I said that this was the largest spring on the Eureka Springs Escarpment. And many of you may not be familiar with the Eureka Springs Escarpment. This is a highly dissected area where that younger plateau and the Salem Plateau, that older plateau, meet. Commonly, our relief in this area is about 400 to 500 feet, though it can even be higher in certain parts of Arkansas. So that Springfield Plateau, it's higher in elevation. It's all Mississippian age strata. So that's our younger strata. The towns of Cassville, Washburn, and Seligman are all located on top of the Springfield Plateau. Now, the lower plateau in elevation is the Salem Plateau, and that's mostly Ordovician age strata and is mostly dolomites. The valley floors of Roaring River State Park are located on the Salem Plateau, and Roaring River Spring itself discharges from the Salem Plateau. Now, along the Missouri portion of the Eureka Springs Escarpment, caves can occur in about 6 different strata. So you can find caves at the very top of the ridge, down at the bottom, and anywhere in between. Our springs in general tend to be mostly gravity springs that really are just coming from a relatively localized area and flowing downhill and discharging from a small cave or spring. Of course, Roaring River is a big exception to that. And this is what the area looks like. It's a very beautiful area. This photo I like because you can very much see the plateau surface here of the Springfield Plateau. And then where we start to drop off of that plateau, the slopes of this are that Eureka Springs Escarpment. And then sort of the valley floors that are sort of out of view in this picture would be the Salem Plateau. We can see kind of another version of this here from Inspiration Point down by Eureka Springs. This is the White River flowing in the bottom here. That's our kind of base level stream for the area. And here in the background, these hills and knobs and top of the Springfield Plateau here, that's that younger plateau, and then our Ordovician strata on the Salem Plateau down here in the foreground. And this is kind of what it looks like on a topographic map. So we've got our undissected Springfield Plateau up here to the northwest, and then where we've kind of dissected into that along the Eureka Springs Escarpment, we have all these ridges and hollows and very intricate kind of little stream networks that are surrounding the spring itself. And so as you drive from the town of Cassville towards Roaring River, you're really on top of this very flat landscape. And then all of a sudden, right before you reach the park, you drop off of the hill down to where the spring is located there. This is where the Eureka Springs is located in the state. This little red line between the blue of the Mississippian limestones and sort of the beige of the Ordovician dolomites. And this red is that line. And you can see it's not a straight line at all. It's very, very intricate. It's going into all these different little watersheds and hollows. And it allows us to be able to find really a lot of caves in these areas. It also continues down to Arkansas. So you can kind of see it here. The pinkish purple is our Ordovician, and then the Mississippian is kind of the gray color in this photo. And then here's kind of a strat column of the area. Now, the very top ones that we see here, these are some Mississippian strata that we really don't see very much. There's actually a sandstone unit in this area, which for this part of Missouri is very rare. We almost have no sandstones in this part of Missouri. It's mostly limestones and dolomites. And so these blue strata are really located in the very southwestern portion of our study area in the highest elevations. The Springfield Plateau strata is mostly this Burlington, Elsie, Reed Spring, Pearson, down to the Northview and the Compton. Now below all that, right at the border between the two is the Devonian Chattanooga Shale. And this is a fairly extensive shale that we see even here in Tennessee, of course, with Chattanooga. And over there, it's kind of a black fissile shale. It often acts like a confining layer or a perching layer. So we'll actually see a lot of springs discharge off of this. In fact, right at Roaring River, even though Roaring River is coming up out of the Ordovician Dolomites, there's actually a small spring that forms a waterfall down into the spring pool for Roaring River. So we kind of have a very small, little perched, localized spring that's discharging water and falling about 100 feet down into the spring pool of Roaring River, which is coming up from 472 feet deep. And then finally at the bottom of the valleys, we have that Ordovician Cotter Jeff City Dolomite, and that's where Roaring River Spring is formed. And if we kind of look at this in a bird's eye view, kind of all this kind of beige and blue is our limestones, our Mississippian limestones. And then you can see as we make our way down into these hollows, we dissect into the other strata and ultimately get down to this beige, orangish Ordovician dolomites. If we zoom in right on the area around Roaring River, again, you can kind of see how all of these strata are exposed along this escarpment. And so when we ridge walk, a lot of times we just follow whatever the best cave-forming limestone at the location is around the ridges, just following kind of these lines. And that Chattanooga Shale, that perching unit and sort of the boundary between these two plateaus is kind of that reddish purplish line that you can kind of see wrapping around the base of these. And then out here is all Salem Plateau Ordovician limestone, dolomite, sorry. Now, we're not the first people to do work here at Roaring River. In the 1950s, J. Harlan Bretz, a famous geologist, wrote the book Caves of Missouri. It was one of the very first books that discussed how caves formed in Missouri and gave a description of the caves around the state. And in there, he speculated about the recharge area. He specifically commented on the diversity of the landscapes between that Salem Plateau and the Eureka Springs Escarpment. He's one of the first people to mention the term Eureka Springs Escarpment. Dye tracing work occurred in the 90s, led by Jim Van Dyke, who was a groundwater hydrologist for the state of Missouri, and Merle Rogers, who was a naturalist there at Roaring River State Park. And this was basically work that occurred in between the busy seasons at the park. Merle was a naturalist, and so he had to give evening programs. He had to work with all the people that were fishing. He had to do burns and all this other work. And so all these traces that they did, which was about 4 dye injections, all were in sort of the December to February timeline in the early 90s. Now, they did 4 dye injections. The largest area that they found that connected to it, the spring, was Upper Dry Hollow, which we'll show you here in just a second. And then 2 of the traces were actually conducted from sinkholes. One was from the Flat Creek area of Washburn, and Devil's Wash Basin was a large sinkhole located just up valley from the spring in Roaring River Hollow. And what was interesting about this is that this does show that the sinkholes are incorporated into the local hydrology. The reason they did the Flat Creek sink was there was actually a old tale about how there had been a large sinkhole collapse in this area back in the 1930s, and that Roaring River nearly ceased flow and then eventually started discharging all this very turbulent turbidity and muddy water and everything like this. And they speculated back in the 30s that this had been a connection between these two, that this had somehow sealed off the spring conduit. And the USGS has also maintained a real-time continuous stream gauge, both along the stream and along the spring itself. There's still one there today. It's located about a mile downstream of the spring, and it works for estimating the spring flows in all but the floods. When you get floods, you get overland flow down a lot of these hollows, and it really spikes the values there. This is kind of what those first traces found out. So here's Dry Hollow. Roaring River is kind of located right here. And Dry Hollow enters Roaring River just downstream of the spring. And they had done a dye injection up here, and that ended up delineating this little area that we see here. Additionally, up in Roaring River Hollow, this is Devil's Wash Basin sinkhole. They got that, and that kind of gave us this little area here. And then out here, we had that positive dye trace from a sinkhole. But that sinkhole had a very small drainage area, and so that's why there's no additional area shown for that little sinkhole. They had done a 4th trace from Piber Hollow, which is located here on Park, but that actually did not go to the spring. And this is going to come important later. We'll talk a little bit more about some of the locations close to the park. So when we first started really proposing to do work at Roaring River Spring, this occurred during the 2017 National Cave and Karst Management Symposium, which was hosted in Eureka Springs. And we discussed this with basically the state park system on behalf of the Cave Research Foundation. And we talked about the need to delineate a recharge area for the spring. There was increasing urbanization. There was a lot of land use changes that were occurring in the area, and it was largely unknown except for that work that occurred in the 90s. Additionally, this will allow the park or other organizations to really target education, outreach, and land protection within that area, because the spring represents the economic engine for this area. It is what brings tourists to this corner of Missouri. We proposed it to Missouri State Parks, and they accepted as a cooperative partnership. And so basically, Missouri State Parks would assist with the charcoal packet changeouts. That was very key because that's the work that needs to occur 3 days after, 1 week after, 2 weeks after, 4 weeks after, 8 weeks after. I live about 8 hours from this study area, and Bob lives about 4.5 hours from this study area. And so having local people that would be willing to go out and change the packets was huge. And so that was how Missouri State Parks was coming to the table. CRF would design the project and execute all the dye injections, providing the supplies, the dye, the charcoal packets, and all that. And then the Missouri Geological Survey agreed to offer charcoal packet analysis to the project. And so this was enormous and allowed us to be able to do this project as a volunteer project. The project began in January of 2018, and we wrapped up in June of 2023. So almost 5 years, a little bit longer than 5 years. We did have a couple of big breaks. Right after we poured our first dye, we had about a 5 to 6 month drought. And then there was something that occurred in 2020. It was, I don't know, I can't remember. It was something that occurred that caused us to take a little break there. But we ultimately did 12 rounds of dye injections for the study. 2 to 4 rounds or injections per round, which totaled 43 total dye injections. So we tried to cover the area as well as we possibly could. The dye injections initially started closer to the spring, and then we worked our way out from there. This was, as I mentioned before, this was mostly losing stream recharge. And so that meant we had to do a lot of significant reconnaissance and sometimes creative injection methods. So we did a lot of driving around on gravel roads and just documenting what the flow conditions were. And so one day, for instance, we drove around the Flat Creek watershed and we crossed something like 55 different stream crossings, and 2 of them had flow. Everything else was dry. And so we used one of those sites as a dye injection. And so, but that gives you an idea of like how pervasive this network of losing streams is. Our injections highlighted many shared recharge areas with Roaring River Spring and other springs. And then we also found that there was significant interbasin transfer. And so what this is we may be in one watershed over here, but because of the karst landscape and the karst development, this spring over here may actually steal water from this other watershed over here. And so we saw that we stole water from the Arkansas River watershed and brought it to the White River watershed, both at Shoal Creek and at Big Sugar Creek. And these are vastly different flow paths if they were to flow overland there. So kind of zooming into what did we do here? We're going to start kind of a little closer to home, closer to Roaring River here. We started close to the spring because we thought, well, this, we're sort of stacking the odds in our favor. Now, we ultimately did 18 dye injections in various hollows and valleys near Roaring River Spring. And here's just a couple of different dye injections that we did. This was a nice day that we had where we had the National Association of Interpreters meeting. We took them out and they actually got to pour the dye. We explained how we do dye tracing, and so you can see a couple of our students there. We actually did enter caves. This is a deep pit cave that was located near Roaring River Spring that goes down ultimately over 200 feet. And you can see, a lot of these little dye injections, you can see they sink almost immediately. And that's what we were really looking for. We don't want to inject dye way up valley and let it flow down valley because one of the ways that we can break down the dye is with sunlight, which is what's called photolysis. And so we like to be as close to where that water sinks into the ground, and that's where we put our dye. And here's a map showing just kind of all the different dye injections, and I know there's a lot going on here. So what we're going to do is we're going to bring in some arrows to kind of help us out here. But ultimately, the main thing is that a lot of these hollows that were close to Roaring River Spring did not go to Roaring River Spring. Even though they were close in proximity, even though we might have been 150 feet above the outlet to the spring, we did not get any traces from all of these different dye injections I'm showing on the map. Now, we did ultimately get 2 different dye injections that did go to the spring. One was from a deep pit cave that I showed in that photo earlier up here. And one was from a tiny little tributary to Dry Hollow over here. And the pit cave, this is the map of the pit cave. And so in that picture, Bob was kind of descending down into this nice little canyon. You come down to an enormous room, but then you can gradually work your way through the breakdown to another pit and eventually down to a water surface here that's about 227 feet below the entrance. That's where we poured our dye. And we think that maybe because this pit cave penetrates all that strata, including that confining layer, that maybe this got us down to the right depth to be able to get down into the spring conduit. Now, Dry Hollow, like I mentioned earlier, was a previous area, and we did a lot of work in Dry Hollow. We did multiple dye injections in tributaries, as well as the main stem of Dry Hollow. The reason we focused so much, A, we had a previous dye trace, but B, when you visit Dry Hollow, you can see that it is a massive, significant losing stream. And so we've put a lot of work into this. We ultimately got 1 dye trace. We believe that the water went to the south and went to another large spring that we'll discuss here later in the talk. But we did put a lot of work into Dry Hollow. I think we did somewhere in the range of about 6 dye injections between tributaries and the main stem itself. Sometimes we just had to do dry sets where we might put a PVC pipe and stake it to the stream bed with the powdered dye inside, and then you wait for the storm event to come along and ultimately inject that. We did get flow in this multiple times. When this flows, it flows like crazy. It can be 6 feet, 10 feet deep flowing down this big channel there. After we found that we weren't really getting dye from the close locations, we transitioned to the west. We went back up that escarpment onto that undissected sinkhole plain, what's known as Flat Creek. And there's a reason for that. You can see it's very, very gentle relief up here. This is that map we saw earlier. So we'd done a lot of work here, but we moved kind of off here to the west. And here's kind of like what Flat Creek looks like. And you can see why they might call it Flat Creek. You can see a long ways on this. This is all underlain by limestone. And if you go to most of the stream crossings, most of them look like this. They're nice losing stream crossings. And we did a total of 10 dye injections in and around Flat Creek, either in the main stream channel or in tributaries to that. Here was our one of two sites that we had flowing water that day. We drove all those sites. But you can see here we actually partnered with the Exeter Volunteer Fire Department. And because we didn't have any stream, they can create a temporary stream for us using a tanker truck. And they can create flow in the stream for about 10 minutes or so, enough for us to be able to pour our dye, which you can see kind of down there, downstream there. And that pushes that dye down into the groundwater system. It gets it out of the sunlight. And then whenever we either time or a storm event comes along, that ultimately pushes it further down into the system. And then here's a dry set being placed in a road culvert. Just want to note the great fashion sense of the Dollar General bag being used as a hairnet there in the photo. And then here is Dylan actually at a Flat Creek dye injection. And what's unique about this is this same location here. And so during storm events or during high flow, we can actually get overland flow here. And the reason we used this site was because we were able to see flow here. We were able to drive around and drive to the next downstream location where it crossed this creek and see that it was completely gone. So we knew somewhere in between there, it was sinking entirely into the subsurface. And that gave us the confidence to be able to inject dye at this location. It also pushed it a little further downstream, which allowed us to say, okay, a little bit larger area drains. So we found that we got a lot of unique traces, and I'm going to kind of try to explain a little bit. We'll bring in our friendly arrows here. And so what we have is some of these times, like I said, we might inject dye here and we drive down to this site right here and it's dry. And so that's an observed sink point. So we know somewhere in here it's sinking underground, turning and going down to Roaring River Spring. We saw the same thing further upstream. We saw the same thing right here, same thing here, here, here. And so this allows us to say, okay, we definitively know it sank right here. Some of these you can see are going to multiple springs. In this case, the dye went from this triangle here at 4.3, went down to here, it sank, but it actually went both to the north and to the south. Now, if we move kind of off to the northwest a little bit, we can see that we also have some dye that's coming from this far northwestern area, all the way from up here in what's called Shoal Creek. Now, there's a couple other dye injections that are off to the sides here. And those are actually going different locations. This one went just to McMurtry Spring right here, didn't go to Roaring River. And this one over here went to another little monitoring site down in Upper Thomas Hollow. Why is this important, even though it didn't go to Roaring River? Because that tells us that there are watershed divides or groundwater divides between those sites and the Roaring River recharge area. So even though it didn't go to our target site, that's very important for telling us that, yes, we're outside the recharge area at this point. So and that's also why we try to have as extensive a monitoring network as we possibly can. Now, why does Roaring River get so much of its recharge from Flat Creek? Well, if you look at this in profile view, so here's the Flat Creek drainage up here on top of the undissected plateau. Then we drop off down to the Eureka Springs Escarpment and drop all the way down into the gorge of Roaring River. And remember, that spring is then another 472 feet deep below that spring outlet. So if you start to look at this, this is an enormous block of rock that could be anywhere from 700 to 900 feet thick that is providing a tremendous amount of storage for that groundwater to supply it to the spring conduit. And so this is a very unique case where we have this undissected plateau that ultimately makes a kind of a big sponge to help feed the spring. Now, one of the other things that we found up in the Flat Creek area was that there was a number of different springs that actually shared recharge with Roaring River. McMurtry Spring, which is also known as the head of Flat Creek because that's usually where the flow starts, shared part of its recharge area with Roaring River. Lee Spring, a teeny tiny little spring, shared part of its recharge area. And then Lee and Brock Spring actually shared recharge with one another as well. And so this kind of gets a little crazy. So when we get down here kind of towards the downstream end of it, we can see that we actually have overlapping recharge areas of these different shared recharge areas. And so this was kind of a unique thing that we really did not expect. And so when we look at these, here's Brock Spring. Brock is kind of in pink here. And then we can see that it borders directly against the Roaring River recharge area. And then down here to the south is our Lee Spring recharge area. And Lee Spring shares its recharge both with Brock Spring, as well as these areas over here share its recharge with Roaring River. So it's a very complicated groundwater system in this lower portion of Flat Creek, something that we really didn't expect to see. Now, we worked a lot of adjacent areas as well, and these are all different streams that we focused on, because one of the things that we like to see, and like I explained earlier, we like to see dye traces that go away from the spring so that we know, okay, we've gone as far as we can in that direction. We now have dye going to somewhere else. And so we worked all these different streams. The ones with asterisks ultimately did get dye traces to Roaring River Spring. I'm not going to go into all these because it's a lot to cover, and we've only got so much time. But I do want to cover kind of a couple neat things that we found both in Butler Hollow, which again, you can kind of see Roaring River up here. We're off to the south here. And then I want to talk a little bit about Rockhouse Creek that's located up here kind of to the northeast of the spring. We'll start with Rockhouse Creek. Now, we were planning to do some dye injections in Rockhouse Creek, and this is the upper portion of Rockhouse Creek. Now, one thing I want you to really notice is downstream of this nice little sinkhole, which has a stream flowing into it, there's almost no stream channel. This almost never has any sort of overland flow to the point where no channels even developed whatsoever. Now, there's also an enormous sinkhole up here on the ridge right behind it that you can kind of see these trees peeking out of. The day that this photo was taken, they had like, I believe, about a 4-inch rain the day before. Everything was flooding, and I drove over to Missouri. We didn't know if we were going to have too much water for doing dye injections, but I drove to Rockhouse Creek, and we were absolutely planning to pour dye into this sinkhole. And I thought, all right, we don't have to get a fire truck. We can just like go over here, pour dye in. It's nice. It's creating a lot of ease for us. Well, we went the next day, and the stream was gone. And luckily, we didn't tell the firefighters we didn't need their help. They still came and helped us out. And we thought, okay, well, we just saw this flowing, crazy yesterday. And so we'll probably be good as close as the fire truck can get. And its hose got to just about right here in front of the tractor. And we thought, okay, the ground's saturated. It's going to make its way over to the sinkhole and get to the bottom and sink. And what we found is we lost an entire fire truck worth of water at the very edge of the sink. It didn't even make it into the bottom of the sink. It took 2,000 gallons of water right at the edge of where the sink formed. And so we were a little unsatisfied with that because we had poured our dye into the low spot of the sinks thinking that like, oh, there's going to be no problem. Well, lo and behold, our farmer that owns this land was very nice and said, hey, I got a couple pieces of culvert up the hill. Let me go grab those. And so he grabbed those. We stuck the fire hose in there, and that allowed us to get the dye all the way out, or the water all the way out to where the dye was down here in the bottom. And so Bob's over here talking to one of the landowners. We got some of the volunteer firefighters. But this is really what this project looks like. It's a lot of talking to individuals. It's a lot of working with volunteer fire departments, the various state parks. It was really this great group of folks who really felt passionately about this area. One of the really neat things about this dye injection was that as the water went down into the sink, it actually created a vortex, and you could actually hear it kind of like almost like you pulled the drain out of a tub or something like that, and it took every bit of the water that we could give it. And so it was really, really, really pretty neat. Then I want to drop down south of Roaring River to Butler Hollow. Now, we're used to seeing these gigantic losing streams at this point, and Butler Hollow is no different. It is an extensive network of losing streams located just on the Arkansas border. In fact, the left side of this photo is in Arkansas, and so we're right there on the border. And we drove this and we thought, man, this looks pretty good. And so we actually did several dye injections in Roaring River Hollow proper. And we had found another little spring, which was McMary Spring, that popped out kind of down valley, created sort of the first flow that we thought we saw. Also, down to the south here is what's called Blue Spring, which is a deep spring located right next to the White River. So we thought, well, this might be interesting. We could get kind of dye either going up to Roaring River, we might get dye going to this McMary Spring, or we might even get dye going to Blue Spring. So we thought it was kind of an interesting area, and we wanted to see how far south we could push that recharge area. And this is my wife Katie walking down another lower reach there, kind of below where we ultimately injected dye. Now, the first dye injection that we chose was a pit, a vertical shaft cave called Mosquito Squadron Pit. Now, I had visited this actually on my 40th birthday because I love mapping pits and especially love mapping pits in southwestern Missouri. And we visited it, and my friend Dylan, who is on the call tonight, had been down in this pit, and he had gone 150 feet in this pit. What's unique is that we are almost at the elevation of the valley floor. So all of this pit, this vertical shaft, is located below the valley floor. And as I'm backing off the edge of that pit, a rock knocks loose and goes kabloosh. And we realized that this 150-foot deep pit had filled with about 100 feet of water. And so this is a very unique feature. I kind of call these sort of these epiphyretic features, which mean they're kind of right at or very close to the water table. And so the water table may come up into them or may drain completely back down out of them. Subsequent to this, cavers went back and braved the depths, and they were actually able to get the full depth of the cave. And so this is everything that was below the water. Now, our friend Dylan went to this cave for us and poured some fluorescein in it for us down the shaft. And what was very, very interesting was this pit went to both Roaring River Spring far to the north and went under the White River, our base level stream in the area, to Blue Spring on the south side of the White River. And this was really, really unexpected. We really did not think that this was going to be the case. We didn't get any dye at our little McMary Spring down the hollow. And this kind of gave us our first connection to Butler Hollow. Now, Blue Spring is one of the largest single springs in northwest Arkansas. It's a second or third magnitude spring. It's about 8 miles south of Roaring River, but it's 120 feet lower in elevation than Roaring River is. It also discharges from the Cotter Dolomite, and it was explored to 218 feet deep by Mike Young in the early 2000s. Our dye tracing ultimately delineated a recharge area of about 18.7 square miles. It was previously unknown, and this is adjacent to and partially shared with Roaring River. And so this is a lot of the dye traces that we ultimately got to Blue Spring. And what's unique is that all of these dye traces that we did went under that White River. They all went below that base level stream. So what that tells us is that there is a conduit that is carrying that karst water from these losing streams to the north under that base level stream and then coming up the spring at Blue Spring. So a very cool setting. This is only a partially delineated recharge area. We're sure that this spring drains other areas, but this was not the main focus of our study. So we only kind of, we got enough to say, okay, we're beyond Roaring River, but it was a really neat kind of side story that we found out. And here's kind of just the flow path showing you. This is another one of these kind of observed sink points where we saw it kind of going down to here and then it turns and goes back the other way to Blue Spring. Now, when we combine all this together, it looks like kind of crazy. There's a lot really going on with this map with all these dye traces. I'm not even going to put arrows on this or try to dissect this. There's a whole lot going on. We're going to take actually most of that off and just show you kind of the recharge areas. And so these are ultimately all the recharge areas that we either delineated in whole or in part. Roaring River Spring, we ultimately found had a recharge area of about 47.3 square miles. Blue Spring was the next biggest that we delineated with about 18.7, but we delineated a bunch of little ones. Some of these around the edges, like Burns Big Spring, which was just over 3.5. But you can see McMurtry up here, kind of this weird double lobe recharge area. Again, very preliminary recharge area. Probably has a completely different shape than we're showing, but we at least know these two lobes do. Then we have Lee Spring kind of in the middle, sharing recharge with Brock and with Roaring River. And then Brock up here kind of on its own, but sharing recharge with Lee Spring. So a very neat area. When we kind of take away a lot of the other noise, when we just get down to the two deep springs, Roaring River and Blue Spring, we can kind of see this is our relationship. And when this is our little shared recharge area here, kind of over to the south, where Mosquito Squadron come from. So summary and conclusions. 12 rounds of dye injections delineated a recharge area of 47.3 square miles. Roaring River Spring mostly drains Upper Flat Creek and a lot of its tributaries upstream from the town of Cassville. This is all mostly through losing streams. There is some faulting that runs parallel to Flat Creek on the east side, and we believe that plays a pretty important role for fracturing that Chattanooga shale, that confining layer, and allowing that groundwater to move through that fault down to the deeper flow paths in the Ordovician aquifer. Now, the deeply dissected hollows of the Eureka Springs escarpment that were close to the spring really didn't contribute recharge to the spring. We think that's due to the unbreached Chattanooga shale and the inability to get to the base of the spring conduit in such a short distance. Can water that's sinking, a mile and a half away, can it sink and go nearly 500 feet below the surface to get into the bottom of that spring? We don't think it can when it's that close. There were a couple of exceptions, Dry Hollow being one of those, and some of these deep pits that were in the valley floor being another. What do we learn about some of the adjacent springs? 3 smaller springs share recharge areas with Roaring River. Some of these are much higher in the landscape. McMurtry and Lee Spring discharge from the Mississippian strata and are 300 feet higher in elevation than Roaring River Spring. Whereas Blue Spring discharges from the Cotter Dolomite, shares recharge with Roaring River, and is 120 feet lower in elevation than Roaring River Spring. So you have a span of over 400 feet of shared recharge areas with Roaring River Spring. Kind of a really neat thing. We delineated 18.7 square mile recharge area for Blue Spring, similar stratigraphy and elevation to Roaring River. 6 traces travel below that base level White River to the spring. And again, that recharge area is just preliminary. But these shared recharge areas really indicate a divergence of flows between these deeper flow systems that are feeding things like Roaring River and Blue Spring and the smaller springs that are higher in the landscape. We could not have done this by ourselves. I specifically really want to thank Roaring River State Park staff, specifically Kelly Koch and Taylor Steinfeld, who changed literally hundreds, if not thousands, of charcoal packets over the 5-year study and dealt with all sorts of questions from the public or people stopping on the side of the road to ask them what they're doing. Mark Twain National Forest for working with CRF on this project, particularly the Cave Research Foundation for supporting this project. Cecil Boswell, who ran all of our packets for us at the Missouri Geological Survey. Again, hundreds or thousands of packets. Crawford Hydrology Lab and Ozark Underground Lab for doing some of our confirmation analysis on some of our packets. And lots and lots and lots of private landowners, both for dye injections, for spring access. We had 2 different volunteer fire departments, Exeter and Jenkins, who gave us provided tanker trucks for dye injections. And then we also had a lot of cavers who came out to help with dye injections, help on talks or any number of different aspects of the project. And so anyways, with that, I think I'm done.